Hello everyone, and we're back to another round of APOW solutions. For information, in case there's any random noise going on, I am now recording this in school, and sorry for the late upload. I have been busy, but I'm done with work basically, so I should be fine now. So next week's upload will hopefully be less than like 14 days away. I think this would be like the 15th day. I mean, technically it's still like within a week if you really were to calculate that, but like if you were to think about it, you know. But like nah, I'm sorry. So anyway, question 1. We don't need to care about 12 a.m. or Singapore or local solar time. We don't need to care about any of that. The only thing you need to care about is birthday month and zodiac sign. And hopefully not Ritzab, okay, that's not important. The important thing here is birthday month and zodiac sign. And because of these two things put together, no, you can cry about it. You should cry about it. You're not gonna see it. And the answer is very simple if you understand what it means, like what zodiac constellation really means. What it means is that, okay, you know the sun, right? Like if I'm an observer here on Earth, the sun will pass in a line, like, you know, true. And like the zodiac, or rather the constellations that the sun passes through are called the zodiac. So if the sun passes through this constellation, it's called zodiac. But as you might know, the zodiac is kind of related with like months and dates, right? So like you might question, why? I mean, that's because at different parts of the year the sun passes through a different constellation. So like for example, right now we're in like February, which means that it should probably be Aries, I believe. Aries. Right now it should be Aries. So right now the sun's in Aries. Alright? So what this means is that the sun is in Aries. So when we are at like 12 a.m. in the morning, technically in the morning, 12 a.m. midnight, right? The sun is in Aries, okay? And then you wait, this is like Aries, an artistic impression. Anyway, and you go to 6 a.m. in the morning, the sun is still in Aries. Just the sun is like rising. And you fast forward to like 6 p.m., the sun is still in Aries, except the sun is setting. So like, it doesn't matter, the sun is just gonna be Aries. And because the sun's in Aries, you're not gonna see Aries. It's when Aries is out there, the sun is out there. And guess what happens when the sun's out there? You can't see shit. So yeah. The answer is just D. There's no, you're not seeing Taurus, I'm sorry. Even if you're born in like, what? May, you're not gonna see Taurus. You try again in like November. And for question 2, which one of the following universe Steph theories is caused by second law of thermodynamics, which is basically entropy, I believe. If I remember correctly, it's entropy. It should be. Let's see, entropy. Or second law of thermodynamics. It should be entropy. Yeah, let's check out entropy. Yeah. So what it means is that the universe likes to be chaotic, quote unquote. Or if you don't understand that, basically means the universe likes to mix stuff together. So basically, it's just gonna get colder, okay? It's just gonna keep getting colder. So that just directly leads to this. I'm not sure exactly what this one is, but I know Big Rip is due to the accelerated expansion of the universe. The Big Crunch is if the expansion stopped and instead like started to go inwards, then just go poof, and the chill is just, you're just gonna chill out basically. Not much to say. Anyway. Question 3, why? The answer for this problem was 4, but it's wrong. It's wrong. Because the answer is actually like 3, but like if you actually think about it, the answer is more like 2. Like I'll explain. So basically you see here, right? Why is Callisto considered better for setting up a base than Europa? Well, this is wrong. Callisto in fact has the lowest surface gravity among the Galilean moons, and in fact I believe that there's not much difference anyway. Like if you just do a quick Google search, right? If we do a quick Google search, Europa gravity, right? We get this nice 1.315, and then we try this. Oh wait, no, that's not what I meant. This is messy. How do I get the Callisto gravity? We can check this out. Right, 1.236. As you can see, Callisto actually has lower surface gravity, and the difference is honestly negligible. No one cares. So this one's actually not it. For less ionizing radiation, this is true. Callisto's orbit is much further. Galilean. I can't spell. Yeah, moon's orbit. Doesn't matter. Let's check this out. Yeah. So as you can see, Callisto is like at the exterior, or like it's like one of the outer, the outmost, right? The outmost moon, between the four, at least compared to Europa. So it actually experiences less ionizing radiation, which comes from Jupiter, because Jupiter is faster and has strong magnetic fields and it's basically just throwing ionized stuff around it. So the further you are away from the center of Jupiter, the less you get bombarded. So less ionizing radiation. This is correct. And the presence of silicates and rocks. Yeah, I guess, but like so is Europa, to be honest. So like it's not really something that Callisto is exceptionally good at. I mean, compared to Europa, kind of. So you could give it, but it's like meh. This is correct because it's once again like further away from Jupiter, closer to Earth, kind of, you know. So yeah, and technically it's just does less gravity lead to easier? Maybe. I mean, it might lead to less damage. I'm not sure, but this one should be correct just because it's like further away from Jupiter, so technically you can travel less. Like if you position your timings well, you know, you can travel a bit less, so there's less fuel required. So yeah, this one should be 2, but it was 4. I think it was avoided, but I don't remember. But anyway, yeah, that's the answer. And moving on to the next page. At what distance from the center of Jupiter, blah blah blah. This one's our first calculation question, and this time I learned my lesson. Okay, I just did everything first, and in fact I have this split screen so we can just search things on the fly instead of, you know, dying. So yeah, we first define our constants. They're not that important, but yeah, we have G, and then the distance center of Jupiter, gravitational field equivalent at Mars. So as you can see, this is equation 2. Let's call this 2, right? Equation 2. And the purpose of this equation is basically it calculates, oh wait, I can do something like this. So this is Mars gravity, okay? Mars gravity, which is that. And then this is the mass of the sun mass. This is just big G, the constant. And then this basically gives you the distance from Jupiter. Wait, no, that's not sun, that's Jupiter, I'm so sorry. Jupiter, yes. This is the mass of Jupiter, and then you can basically just do some basic, you know, like math, and then you just sub n in, since you know the Mars gravity, and then you just get this distance, and you convert it into scientific notation, so you get like, you know, 1.88 times 10 to the power of 8, which is like approximately b. It's a bit of discrepancy, but it's like close enough, so all's good. But yeah. And then when you look at question 5, you ask how many of the following exoplanet detection methods can accurately determine the mass. The answer is no, you can't. None of them. And in fact, this one is not a method, and this one is also not a method. They're far from it, okay? Black body radiation is, as its name suggests, black body radiation, I guess. There's not much I could say about it. It's radiation of a black body. Yes. Yeah. And then as for relativistic beaming, it comes from like pulsars and black holes and stuff. You know they have like beams and things. That's what it is. It's nothing to do with exoplanet detection methods, basically. And when you look at radial velocity, which basically determines the wobble, or rather you measure the wobble of the primary star due to the gravity acted on it by the secondary satellite, and then the transit is basically just thing passing through, right? Covers it, and then the luminosity of this thing will drop, or the magnitude, whatever. And direct imagery is just direct imagery. Just take a photo of it. This one definitely will not give you the mass. It's literally a photo. What do you want to do with a photo? Radial velocity kind of gives you the mass of like... Actually, it's a bad question. The mass of what? Radial velocity can give you an estimate, but not really. Because you don't know the mass of this. You don't really know the mass of this. I mean, there are ways to calculate it, surely, but like, you know. And So in most estimates, it's not accurate at all. It's estimate. And similarly, the transit method also suffers from similar things. In fact, the transit method is more commonly used for radius estimates, at least with respect from the primary and the secondary object. But like, yeah, basically, because of this, key term here accurately, it's nothing. No, you can't. So yeah, moving on. Which of the following can be the decreasing aperture and keep focal ratio? So it's like you have big beam, you have like smaller beam. I don't know why I like drawing it like telescope light cones like this for some reason. Yeah, aspect ratio stays the same. It's just smaller. The answer here is lens sagging, which is basically just the telescope itself deforming because of how heavy the mirror or the lens is, and it makes a lot of sense, like it's heavy, man. The middle, or rather the inside of the telescope is just empty. It will sag when the mass becomes unbearable, which is also why you rarely see huge refractors and why they're often very expensive, because lenses are much heavier compared to like mirrors. So yeah, these are corrected by having longer focal ratios most of the time. Oh wait, no, chromatic is corrected by like having like correction lenses and stuff, because this one's like a lens problem and it's due to the RGB values or the different wavelengths of different wavelengths of light. They reflect slightly differently. So example, if you have like red, green and blue, right, like it's not gonna be an exact match, you see. It's gonna like be a bit like this, It's not an accurate drawing at all, but you get my point, right? Like it's not gonna be exactly focused on here and there. It's gonna be a bit off. Which is why you see like sometimes you see like red on one side and blue on the other, which is why you have like corrector. So basically lenses that fix this problem or stuff like that. But like it has nothing to do with aperture basically. So nah. And this one is the fix for these two is longer focal lengths, not like decreasing apertures and keeping the focal ratio the same. So like, nah. C. And by longer, I think in general longer is better, but like if you want to compare it with the same aperture, then you would require to have like a longer focal ratio, since the F ratio is just focal length over aperture. So like, yeah. And for question 7, which one of them is the rarest? It's a generalized question, wolf-rayet star. Just know it is. Alright? Just know it is. They're rare stars. They're explosive and powerful and rare. Not much to say. Question 8 is this one. This is the Chandrasekhar limit. I can't write the word, but it's for white dwarfs. Yeah, it's not neutron stars. And the neutron stars, so like neutron degeneracy. Once again, it's white dwarfs that's held up by electron degeneracy pressure. So B would be correct if you're asking for like white dwarfs, but like D is correct for neutron stars. Yes. Moving on, we have this, peak wavelength. Once again, it's a calculation question. Let's move on. So it's like 225 nanometers and its radius is so on. Find luminosity and solid luminosities. So for this question, our approach is once again quite simple. I define B here, we don't care, as a constant. So this up here is the temperature. Because we use Wien's displacement to find the temperature. I'm using small t because like it was a bit annoying to type, like make this bigger, so I wasn't bothered. So yeah, temperature of the star is this much, in this equation. Constant, don't need to care. This one is constant, don't need to care. This one's Stephen Boltzmann constant, don't need to care. This one is the luminosity of the sun because they asked it compared to the sun. And this one over here is Stephen Boltzmann law. So basically just sub in everything, right? And then we make it over the sun, right? The solar luminosity, because the solar luminosity of the sun is what we're comparing it to. So yeah. I don't think we provided you with sun's luminosity, so I think you're supposed to know. But then they did give you solar constant in the SAO formula sheet, so technically you can derive sun's luminosity, but like, yeah, for me, I just memorize. It's good to memorize. Same for the constants, but they're provided, so it's less of a problem, but yeah. Anyway, so you get 158. Another method you can try is you can think about it. So fun fact that the sun's peak wavelength is like 500 nanometers, and its surface temperature is like, or is it 7, like approximately this much? Doesn't matter. The thing that matters is approximately like 500 nanometers. So if you remember that, you can basically substitute in the sun's radius, which is given, and the peak wavelength, which is something you memorize, and you can come across to like a close enough answer. It's not exactly 158 as this would give you, but it is like good enough, so it's acceptable. And question 10 is once again another calculation question. In this case, you use parallax, d equals 1 over p, where p is in arc seconds and d is in parsecs. Alright? So this approach here is basically you just take... Okay, so they gave you the... First you find the distance in parsecs. They gave you a distance of this thing, right? This is this much light years. When you convert it to parsecs. So first you convert it to parsecs. And then you find the parallax, which is going to be this much. In my opinion, I really don't like this equation because I keep confusing like p for parsecs. I don't know, man. But like, yeah, it's parallax. Regardless, so you found the parallax of the expected value, or the literature value, which is basically expected value. And then you find this thing in arc seconds. So since it's given degrees, remember, 1 degree is equal to 3,600 arc seconds, and you convert that over, and you get x. I just call it x because e is taken, like, e is like experimental, yeah, but e is also Euler, so yeah. Anyway, then the formula for percentage error is basically just the value you got, right? The measured value, I just call it n, minus the expected value over the expected value. So you just sub that in and multiply by 100 to get like the percentage, and then you will obtain a plus a. So yeah. Also the keyword is parallax, not like distance. So that's why it's positive. If you do it the other way around, you actually get like negative, I believe. So yeah. And for question 11, this does not seem that much like a calculation question. It's not a conventional calculation question. I personally also don't really like this question because I'm pretty confident that we did not give you enough like constants and stuff, even in the notes, I believe. So it's not a good question. But this is probably how you would solve it. So first you find its absolute magnitude, find absolute mag, right? Negative 26.5. And then you basically calculate how much of it is compared to like the sun. So it's approximately like 3 times 10 to the power 12 like solar luminosities. L sun, right? And then they give you the mass already, right? So you can just find the mass to luminosity ratio, which is basically just mass over luminosity. Except in this time L is m because m for magnitude. It's weird. I'm sorry, it's confusing the way I name things. But like let's just roll with it, alright? And so you get the ratio for this cluster, which is like 1 to 6. And then if you sub in literature values for Milky Way or estimates, which is basically tells you that the mass is like 1.5 times 10 to the power 12 solar masses, and 1.5 times 10 to the power 10 like solar luminosities. Since they're all in like solar same units, you can just compare and you realize that this one actually has a higher mass to luminosity ratio, which also means that it's more dark matter. But because like dark matter is like provides for mass, right? So when you have a higher mass to luminosity ratio, you need to have more dark matter. And also just because you already have more mass, right? Because there can be a case where it's a higher ratio but a lower mass, correct? So maybe if this is like maybe like 4 times 10 to the power like 8, so like, you know, 10 to the power 8 is like less than 10 to the power 10, right? So like, yeah, it wouldn't, or wait, no, 10 to the power 12, right? So in this case, the 10 to the power 8 would obviously have less matter. So even though it might have a higher mass to luminosity ratio, it's still gonna have less dark matter just because it's like less matter like overall, you know. But like in this case where it does have more matter already, it's B. It's gonna be B. Moving on, we have question 12, estimation question. So this one is also weirdly phrased, but basically they're just asking you to find synodic period. So it's just like 1 over the what is this? The outer, the inner one, inner minus over outer, or is it? Give me a second. Yeah, I think it's the inner one. Yeah, the inner one minus outer. So yeah, basically, or just minus and just flip the sign over. Yeah. So how do you do this? So the theory is circular, right? So you can just use the powerful tool called mmv squared over r equals to gmm over r squared. Do some cancelling, you get r here, right? Or rather you get r up here, right? Cancel this, you cancel this. So you know v squared, trying to find r, right? So r is just equivalent to gm over v squared. So you can find the radius for both of these orbits, which I found up here in A. And then I find the period using Kepler's third, because you know this one's just equivalent to square root 4 pi So you substitute this in, you find the period for both. And since you know the period, you can just find the synotic period. But don't forget, this is in seconds. They asked in years. So you divide it by stuff. And you get like 5.62, which is exactly 5.62. Beautiful, right? And over here, you have estimation question. This one, I don't like estimation, never liked estimation, but what you need to know is just the PT5 has like a radius of like approximately like 5.5 meters. And also, it has like, it orbits around like 4 times the Earth-Moon distance, which matters because this would explain the divide by 4 down here, because it's like a bit further. Actually, if it's 4 times the distance, it should probably be more like divide by 16, I feel like. Because the answer that was given is like 1.53 times 10 to the power of 11, I believe, which is similar enough to this as well. Because like according to Google, that's its orbital distance, 4 times the Earth-Moon system. But like since brightness is inverse square, technically this is like 16, which is like 3.91 times 10 to the power of like 10. But like it's an estimation, so like it's like close enough. So if you aga, it's like basically like they're just like tickets 1 times 10 to the power of there. So even if I do multiply by 10, it's still like at around there. So it's alright, I think it's alright. And just like that, APOW 12 is finished, we're done. I hope you enjoyed it and see you all next time.